this is a discussion, very informal. It's not a lecture. It's not what, just informal discussions about some of the concepts we come across in our studying mathematics. But my idea is to try to see if we can see, I don't know how far we can go backwards to try to study mathematics in a kind of way that at the end of the day, we end up with a kind of a system, meaning kind of connected, some kind of connected components of one thing, body we can call mathematics. And then we just try to see if we can start from the most primitive thing. But in this case, at this stage, we'll assume that the concept of a set is something we are well versed in. It's been cleaned up with all the controversies or paradoxes and everything. Then we just assume that we understand what sets are. That's the thing. So I don't know, maybe I'm allowed to say this kind of controversial thing. A set, which I can maybe call a raw set, raw as in raw. A raw set is simple, some kind of chaos. What we know that if X is a set, what is sitting in X there are elements of X, and just being a set does not tell us that how elements of X are related or how do they interact and everything. So it's just something which is like raw. That's what that is. But we want to start by talking about sets, elements of a set interacting. And once we talk about elements of set interacting, then that takes us to kind of operations. In other words, we take maybe two elements of a set of X, let's say X and Y.
Yes.
We've got here X and Y. Then we just choose to interact, to make an interaction between these two things of any way. For example, we can just say X square Y. What square Y in this case doesn't matter, but we just know what matters was that these things has interacted in a certain way. What is possible that this interaction can result in another element of which is called Z, which could be Z, an element of X, or Z, which is not an element of that. Okay. So if we do this thing and then the result jumps out of X, then that's kind of a problem. That's kind of a problem. Then for example, let's, of course, at this stage, you assume that we know some operations, like the basic operations we do at school. Like, for example, if we say that, okay, X and the Y are natural numbers. In this case, we're going to choose which type of natural numbers do you want. Do you want to start at 1 or do you want to start at 0?
Let's start at 1.
Let's start at 1. So
sorry to disturb. You know when you put that box like that, now I'm reminded that it's more like a trial and error of choosing what operation should be there. Yeah. Now that I'm thinking about taking it back.
I'm just saying there's an operation there, but in this case, we will just define clearly what it does, but we know that it is an interaction between the two elements which produce another element. Or maybe it doesn't produce anything, but in this case, they say it produces another element Z, which could be that or
not.
Or it could be Z is there or Z is not there. So if we take an example of natural numbers, like you chose that, okay, let's check natural numbers. We start from 1, 2, 3, and so on. So we know that if we take this kind of an operation, this will always be a natural number.
Yes.
And then if we take this, this could end up giving us a Z, which is either Z, sorry.
In this case, do we choose, what do we say? Do we say that X is more than Y or what? We're not there yet.
I'm just saying that if we take any two natural numbers and add them, that will be in there. But if you took another operation like x minus y, this z which ends up here, it could end up in two cases that z is in that, and then z could be not in that. We know that. We know that for a fact.
Yes.
This is what maybe the teachers would say it can't, or what. When you can't get an answer which is natural, and say we can't. We can't. So for example, if you say 8 minus 9, they'll give you this slogan that says it can't, which is kind of a very bad slogan, because when you say it can't, you put a full stop. There's no further exploration to be done there.
Yeah.
So possible, what is better to say is that we are not yet having enough kind of tools to deal with this. Then
in that set,
then maybe it should be pegged. But in the case of plus, every time we add n and that we get a natural, then we'd actually say n is closed. Respect to the operation plus, it is closed.
Yes.
But you find that this operation is possible. If we're taking 9 minus 8, then the answer here will actually be a natural number. But if you take the other way, it doesn't. Then we'll say then this thing here, the natural numbers, these natural numbers, this set is not closed. With respect to minus.
But in this case, do I need to specify? I mean, do I need to take into consideration how they are ordered?
No. In this case, we're not worried about the order. We just want to say, if we operate this way with natural numbers, we always get natural. If we operate this way with natural numbers, we might get a natural number, we might not get a natural number. So in the case that this happens, which we know it happens, we would say that this set is closed. And in this case, this is not closed. That's what we think. So what I'm going to the concept which is coming up here, what does it mean to be closed with respect to a corporation? So if it's to be closed with respect to a corporation, means that whenever we operate with elements of that set, the result it isn't. It cannot jump out. Then if the operation results in some things which jump out of the set, then that operation, that set is not closed with respect to that cooperation. So in this case here, the concept which must be left sitting square is what is to be closed with respect to an operation. An operation is any manipulation you can do or any interaction you can do between the elements of the set. In this case, we call this addition, like we know. We already know this thing is addition, and then the other one is subtraction. Yeah. So this thing is closed with addition, is not closed for that. Then maybe that takes us exactly a set. We said we already understand what a set is. So then that takes us exactly to what is a magma. And now we've also got an idea of what is an operation. What could be an operation?
May I ask something? Maybe let's go back to the previous one. Let's see. So if it is not closed with respect to minus, and then do we? I'm not sure. Do we say that it's open because then now we have to need more help from other things?
It is not. It's not closed with respect to what. The only thing which could be maybe we can do, which I didn't want to mention now, is that maybe, or what that thing is basically indicating is indicating a limitation of the natural numbers, because this operation can be done in a restricted way. But it could be possible that we want this operation to be done in a less restricted way, which meant then, if we were to talk of the universe of numbers, it would mean that this thing is too small to accommodate this. Then we would think of ideas of extensions. Okay. So we're going to pick this thing of extensions for now.
Okay.
Okay. So that's why I said it is not good to say here it can't. So if it can't, you are closing, there's no further explanations on what we do. So what we do when this gives this message that it can't, we only see that it is limited in terms of that operation. Then what could be possible maybe to find a possibility of doing this thing is to consider extending. Now considering a bigger universe. And then the question which will fall now, which maybe we'll do later, is how to actually extend this set of what?
Of natural.
Yeah, in such a way that the separation can always be possible. Okay. So then, here talking about the closedness of a set with respect to operation, then it takes us to what we call a magma. A magma is a set. As we've said, we've already understood what saying. We already said we take that the concept of a set and what can be done with sets is understood. There are no controversies, this is nothing. So magma is a set. So if we say X is a magma, we simply mean that if it's going to be a magma with respect to a certain operation. Yeah. So if X is a magma with respect, or maybe let's rephrase this thing, to say X is a magma.
Because the other question that I wanted to ask was that how does it differ from the other sets?
Yeah.
That's what I wanted to.
You see now, first of all, we said a set is a raw set without any kind of operation, no kind of interaction. We should just say it's a raw set. It's a raw set. So, but when we went in natural numbers now and introduce an operation, we're now not really talking about a raw set. We're talking about a kind of a structured set. There is a structure, and the structure is brought by what? By bringing together the set of natural numbers, the raw one, and an operation, which will make an interaction
between the elements.
Yeah. So now here, when you do this thing, now you can talk of something like this, and then later what we can do, we can actually try to study what are the really things which happen here, and these things when they interact, are there any kind of patterns they form, are there any kind of the laws they respect, and whatever. Then we can start talking about a natural number being a magma or not being a magma or being something else. Then we say a natural number together with additions, they form such as a structure.
Sure.
So then here, basically, we are sort of coming up with a structure. A set alone, no operation, nothing, just elements alone. It's just a raw set. But once you start coming up with the relations, maybe operations there, we're starting to come up with a structure. So basically, in this case here, what I'm trying to do here, a magma is a kind of a fixed structure. When you say X is a magma, we mean actually means X is endowed with an operation. So when I write this operation here, I'm not talking about addition, I'm just talking about any operation possible which can be defined to make sense in that we don't remember such that this X is closed. So when I'm saying it's closed here, X, comma, this, meaning when I operate with this thing in X, everything falls back in X. Nothing else. I'm not asking for anything else. You understand? So that's a magma.
So a magma should always be closed.
The magma, the operation is closed. But there's nothing else we want.
Okay.
So basically what you can say for maybe this is the most primitive kind of a structure. All what happens is that these things interact and then they produce one of their own. Two of them interact, they produce one of their own. Interact, produce one of their own.
So it doesn't matter what operation we choose.
Yeah, it's just about what you choose.
Okay.
So can you think of something, or even look at the sets you know, and you try to see if you can come up with this set, and then try to see if you can kind of create a magma of your own. Try to, I mean, the examples which we know already, in this case, they're very useful. You can think of natural numbers. Think of natural numbers. Think of them in a broad sense that, okay, these are natural numbers. 1, like we agreed that we're going to start with 1, 3, and so on. Maybe this thing is a magma, with respect to which operation that's what will happen.
It's a magma with respect to addition. But then if I want to check with respect to subtraction, it's not a magma. Is it the right way to do it?
Yes.
All right.
With respect to addition, it is closed. We don't demand anything else. We don't demand anything. We just want to see the elements of this thing. They interact and produce something in the magma. So with respect to addition, yes, it is a magma. But let's suppose now we take a subset of this, and we say this thing here. Let me just do this thing. Maybe this thing has never been written somewhere, but I'll write it myself and say odd natural, which means that I'm wanting not natural numbers, but I want odd ones. Which one are the odd ones?
I will start with 1, 3.
1, 3.
5.
5.
7 and 7 and 9. I'm not sure how far should I go.
No, just examples which are going to give you enough idea what to talk about this now. So this shows that we're doing with odd numbers. Yeah. So now, is this a magma with respect to addition like this one?
No.
Why?
Well, if I add 1 and 3, I'm going to get an even number.
Exactly.
Yes.
Exactly. 1 plus 3 will not get us to
odd
naturals. So it's not a magma.
Okay.
So now.
Okay.
So now.
Okay. Are you going to send me the video?
Yes. Okay. So there it is. You now know a structure, one structure, magma. Clear? And you've got an example of a magma. Natural numbers. You don't demand anything. In this case, you don't demand anything else from the number. You just want to know that when you operate with this thing, you get a magma.
So there's actually no two odd numbers that can give me an odd number. Like when I add them. I never thought of it. I never thought of it.
What is that?
I mean, if any two odd numbers, when you add any two odd numbers, I never really thought that maybe there's any one of them that can give me.
But do you know how to represent an odd number? Let's say
2k plus 1.
2k plus 1. Let's test that. So let's say one number k prime is equal to 2n plus 1. Which other odd number do you want?
Which other odd number do I want?
Let's say k.
So I have to represent it in a different way than that one?
You can just give another expression of an odd number. Isn't it 2n minus 1? Is this an odd number? This is an even number, isn't it?
Yes, that's an even number. Yes.
So then let's add the 1. This is an odd number. These two numbers are odd.
What is it? Oh no.
These two numbers.
So basically this is the same as just 2n minus 1.
Yeah. This is a number n. A number n minus 1 is before it.
Yes.
So if I multiply by 2, I get an even. If I add 1, I get an odd. If I multiply by 2, I get an even. If I add 1, I get odd. So the question you're asking if I add any two odd numbers, what
can they give me any other odd?
This is what I was checking briefly.
Tell me. We forgot one of the ones.
Which ones?
Oh.
This is n minus 1. Oh, here, okay. Okay, yeah, this one. Yeah, 2n minus 1. Yeah, I'm right. You're right. You're right. So if we now add these things, we need to remove brackets here and say
Yes.
2n minus 2 plus 1.
Yes.
And this side say 2n plus 1, which will give us 4n,
Yes.
like 4n. 4n plus 2. Plus 2.
Minus.
And this one gives us 2. And this one minus 2. And this is a 2n. It's even. So you can, I don't know what you want to conclude yourself.
That's it. There will always be.
It looks like
There will always be.
So we found 2 odd numbers which don't give us an even
I really
number.
never thought of it.
Yeah.
Yeah.
So
Ask myself.
So can we say now a one's first structure of code is a magma, and you know what happens in a magma. There's an operation, the operation is closed. That's enough, nothing else. Maybe then if we later become more maybe stricter and impose more operation, apart from being closed, and impose another operation, we're creating a new structure. We're not going to call it magma. Otherwise, we're not going to, then there's no development. If we're going to impose new rules and whatever, we say, okay, this is a game, we've got these 2 rules, we increase the rules, it's a new game.
It changes.
Yeah, it changes. So we're fine with the magma. Okay. Let's then say we're given again x, a set, and then we want to, don't really know this. You must check this word when people say endowed. It's a very popular word in mathematics. Endowed with an operation.
Okay.
A set endowed with some operation. Let's say symbol for the operation. So remember we said the operation was just simple describing some form of interaction between the elements of sets producing another set, producing another element, which could be possible in the set or not in the set. Okay. So let's look at what do they mean by endowed meaning. Sometimes it's good to have a common man's understanding of a word, and then try to figure out why is it used this way in mathematics. So what is the name? It says provide with a quality or ability. In order to endow is to provide with a quality or ability or asset. Give a what? A bequeath, an income or a property to a person, to an institution. So in other words, you've got a set, then you kind of provide it what? With a certain quality or an ability to do something. Then you say the set is endowed with an operation. Something like that. So let's go back here. So when we say set is got in equation Pascal, what do? We end up with what this, and then this, instead of being just a set, it becomes a structured set. Then we then might maybe put some kind of rules or laws. How is this thing defined? And then maybe there will be additional properties of what it calls and so forth.
So magma's structured, are they all structured?
Yes, magma. When once you say it's a magma, now we're talking about the structured set. We're not talking about the set, we're talking about the structured set. So what are the rules on magma? Is that operations, interactions of 2 elements with this operation, it must give us something in the magma, in the set. So now what we're going to have here, we're going to have 1. What do we want? 1. We want that x is closed with respect to this operation. That's what we want. In other words, now here what we're doing, well, basically maybe like you can say we're giving the axioms which this structure must kind of respect. Yeah. So the other thing now is that this thing here, First of all, before I talk about this thing, if you had bricks, this is the brick A, and this is a brick B, and then this is a brick. This is a brick C. That's a brick C. So if I were to ask you to take these bricks to somewhere here, and they say to you, take them in twos. If you take them in twos, probably what you're going to do, you're going to get A and B.
Yes.
So you make a bag, you carry them. And then later, maybe you come and get C. Because they're not two, but the bricks have got to go there. You've got to do that. So that's one way of taking.
So I take them by two, but I don't have the. I'm not sure if this is going to be.
You don't have an option to take them three.
I don't have an option to take them three.
Yeah,
but I don't have an option to take one bag so that I can have two again.
Yeah.
I can't do that. You understand what I mean?
I think you don't have an option to take two. You don't have an option to take. If you're given instructions that take them in twos, it's most natural that you're going to pick two and go. But when you come back, there's one. There's no option except to take the last one. You understand what I'm saying? So if this is the first option, so another person in the same way could have taken this B and C, put them in a bag, and go. And then last he comes and take one. If you check what has happened here, the order of the bricks is still the same. There is still the same. But the thing is, that task has been done. By doing this, it's doing exactly the same task. So
just differently.
Yeah. So we've done the same thing, but the way we took the things are different. Do we expect these bricks to be different when they get here? No. You know, it's what I'm trying to say. Carrying these bricks in this order is the same as carrying these bricks in this order. So it is, if things are the same, this is the symbols we're going to use to say they're the same when you call it equal. But this kind of combination
I actually wanted to ask you.
It's describing what you can call associativity.
That's what came to mind. Is that how they came up with it like that?
This is what you observe when you add natural numbers. This is what you observe when you add integers. This is what you observe when you multiply natural numbers. This is what you
but definitely not your rationals and what.
I'm not sure.
No.
I'm not sure.
No. Sorry. In this case, we're not talking about multiplication or anything. We're just talking about.
No, we're talking about any operation. We're talking about any operation.
Okay.
Yeah.
Okay. Sorry, I was confusing with.
So in this case now, what I'm trying to, with this kind of nonsense I'm talking about here, I'm trying to tell you that in a structure like this one, whereby if I get three elements in the set there, we have that A box B. This thing of two, we talked about two. Two, in other words, at a time we can operate it only two. Then we're saying this is a binary operation. It doesn't allow you to operate it three at a time. You operate it two. So when we put three elements X, Y, Z in X, first of all, we say it's closed, which means up to here, it's a magma. But we're adding an additional story or additional data that if we take any three, X, box Y, this is now one thing. And then box Z. Brackets and Z is binary. This is one Z. And maybe this produced Z prime, I don't know, but it produced something. So now I'm left with two things. When it becomes the same as this.
In this case, what are you doing? Are you building properties for that structured set?
I'm putting a property in the set. Okay. We're posing a property in the set that we require that this thing could behave like these bricks.
Okay.
So if we require that, it will then say X box Y box Z. So this we know it's going to produce 1. It's binary 1, 2. Operating 2 produces another 1. And then this 1 produces here, interact with Z, will produce something else. So if this is the same as saying X box Y that, if that is that, if this structure is a magma plus the operation, if satisfies this, then we're going to call it a semigroup. I hope I'm not making a mistake here.
Oh, okay. So that I remember what we're doing here. Okay.
That's going to be semigroup. What's happening here? It's closed. The two things, semigroup. One, X is closed, and the operation closed with respect to that box operation. And the box operation is associative. That's what it's doing. So when you do that, then we've got a semigroup. Then what you can do now, you can check the sets which you know, like addition, like natural numbers. If I endow it with plus, if we endow that with plus, is the plus going to do this? Is the plus going to do that?
Yes.
So this is it's got a new structure. Apart from just being a magma, it's a semigroup. And what if I give you the real numbers with a plus?
So in this case, I'm allowed to choose any, just any.
No. Actually, this is I want to say, let's say positive real numbers.
Because I'm thinking that if they're just real like that, they are a bit big. So the set is it not like big?
It's big, but okay, if I pick in 2 real numbers and they add them, they are positive. Am I going to get positive real numbers?
Yes.
So it's closed.
Yes.
So it's a magma.
Yes.
What we must see here now is that if we call the magma a primitive structure, when you become a semigroup, you don't actually lose your primitivity. Your primitivity is still embedded in you. So the things which you had in primitive stage, they're actually embedded in your system. So we still here.
More like they form a foundation or some sort.
Yeah. If we just concentrate on being closed, this is closed, so it's a magma. Is addition going to be associative? Yes, it's associative.
Yes,
so it's going to be a semigroup altogether.
Yes.
Right. Let's come to something more interesting here. I'll start first of all by talking about words. Words, what we do with words, taking a typical kind of situation, we basically got what we call the alphabet for the words. Because we need an alphabet to write words. A, B, C. But you mustn't forget, what we're trying to do here, we're trying to explore mathematics, mathematical concepts.
Yes.
So, X, Y, and the Z, those are alphabets. So whatever I write in any sequence using these letters is a word. So I'm going to call my word 1, A, B, D. What it means is not important. Important is that it's a word. The word is a sequence of letters of the alphabet. And then you assign them a meaning. You assign them a sound first, then you assign them a meaning. And then word 2, I could say,
CXZ. I don't know.
Yeah, CXZ. Yeah, doesn't matter. CXZ is a word. And then I want a word here which I'm going to call word 0.
Okay. How do you define that? Okay. What does that mean? Does it mean you're allowed to choose any 3 letters?
I'm not allowed.
I'm not choosing anything.
I'm not choosing anything.
Okay. Okay. Word 1, I don't choose anything.
If I'm supposed to say something, I say nothing. If I'm supposed to write, I write nothing.
Okay. The silent treatment of some sort.
Yeah. So let me call this thing an empty word. Empty in the sense that it doesn't have characters of the alphabet. But what I know is that if I take word 1, word 2, put them next to each other like that, I'll get word 4, word 3. In this case, word 3 would be A, B, D, C, X, Z. That would be the meaning I will check in the dictionary. And if I put word 2, as you can see here again, it's binary. If I put word 2 and the word 1, I'll get the one to C, X, Z, P, D. It's a different word. There's possible this is word 5, word 4.
But then if I put word 1, word not and word 1, then I'll just remain with word 1.
Okay, that's nice. Then if I put word 0 and word 1,
I think I'll remain
and
with word 1.
in this case, even if I put word 1 and I put word 0, I get word 1. And it looks
Word
like
1 with
any
nothing.
other word here with the word 0
Get that
plus
word.
and word 0 is going to be equal to word 0 with any word. And this will be
Just
that word. There's something interesting here. So then I can now remember this is simple. You see, I can look at this thing as a set, and as a set here, from this set I can create words. So if I were to look at a set of words, this word 0 will be there. So the word you say is nothing. Which when you write nothing. And everything.
Yeah.
So I'm seeing something here as set X. And the other thing, let's check everything we checked before. We saw that this thing is a binary operation. You know, I'll call it cascading. Cascading. If I cascade words, I get a word. Well, I put 2 words next to each other, I get a word. It's just a sequence of characters. Whichever way I cascade them, I get a word. So, which means this is now kind of an operation. Let's just put it abstractly and say that operation is this. So, if I'm saying word 1, box, word 2, I'm just simply saying put word 1 and the 2, one after the other. Then I get 1, word 3. But then I'm seeing that if I've got in this set here of words, I've got a special word. Which one?
The empty one.
The empty one. So the empty word belongs to this set. But the empty word, let me just put it this way. E. Let's just say the empty word is E.
Am I allowed to put word 3 with word 1 again?
Which one?
With word 1 again.
What do you mean word 3?
Am I allowed to put word 1 and word 3?
To operate with them? Yeah. If the operation is an operation on the set, you can operate with any of the 2 in the set. So I'm taking word E and then operating with the word 1. What we've noticed that this will give us word 1, and this is the same thing with the word 1 operated with E. And any other words. Now this is for all words in X. E operates with that word will give you that, and it will be the same as that E. Then this word E deserves a special name. It's a neutral word. So now X
It
as a
doesn't
word.
necessarily make changes.
Yeah. X means this as a set. If we look at it as a set of words, maybe this is just an alphabet. No? Then for the set of words, let's get another new thing and say, put it like it's X bar. Obvious. You must notice that in this set, X is in as a subset. Why? There are words you put one letter altogether. So all X and all combinations of the other, they are words.
So the more we add things, the new set becomes much bigger than the previous one.
Yeah. So we've got more things now in X head there. But what you can see with all the things in X head, if we take like B there as a single word letter and you combine with an empty word, we're going to get B.
Yes.
And if we say B combined with an empty word this way, B combined, this is an empty word combined with B, we get B. Now this is B combined with, cascaded with E, we still get B. And then we're saying this thing here, E, is called a special element, a special name, let's call it a neutral member or neutral element of X. Wow. But if I've got A as a word, B as a word, D as a word, it will also actually follow that if I get A cascaded with B, it's a binary operation, and then cascaded with D, it is clear that this thing is going to be the same thing as B cascaded with D, and then cascaded with what? Because what is this going to give us? This is going to give us AB.
Yes.
What is this going to give us? This is going to give us ABD. And then this side, this is going to give us BD. And when we operate this one, going to be ABD. So that's that. What does it say? He's saying there's associativity. Okay.
Yes.
So in X bar, the set of words, there is in X bar, you have to endowed with our operation. So now a set is not just a set at standalone, it's a set with an operation, then it's a structure. So this is a structure, and this is a structure.
So it has to always go.
So what we see here in this structure, we see in X there's a special member. In X bar, in other, among the words, there is a special member. E called the empty word. What does it do? We cascade the E with the N word. We get that N word. We calculate that, we cascade that N word with E, we get the same word. So then E is a neutral element. Next thing, in X, obviously this thing is a magma. It says close compared to this operation, if we just emphasize that it's close. But it's richer. It has got a new thing here, which just operates with the thing. You don't see nothing, it's like doing nothing. And then this is associative. In other words, given, word 1, word 2, word 3 in X bar, what happens here? Word 1 cascaded with word 2 is an element of X bar. But you cascade that with word 3, you see that this is same thing as word 1 cascaded with word 2 cascaded with word 3. So this is one entity.
Yes.
So it's associative. And then we've got three axioms here now in this structure. One, closed. Respect to the operation. The operation is always binary. Né? We must know. We've talked about it, maybe we didn't emphasize much. That's binary. The next thing, given word 1, word 2, word 3 in the set of words. Always word 1, and then exists in a special element E called the empty word, such that for any word in this E cascaded with omega is equal to omega equals to omega cascaded with what? E. So maybe the exercise which you must try to find out here, to try to prove, is that if such an element exists, can there be two? So we can prove that if it is a neutral element in this waiting operation, it's one, or there may be two, or there may be three. Out here. So if there are two, then we'll say there will be neutral elements.
Okay.
Maybe that's going to be another structure. But this structure just described here was simply saying that X and X bar endowed with this operation here is a monoid. That's a monoid. Let me see what I wrote in the group. Let me see what I wrote in the group.
What you wrote in the group?
Yeah.
Oh, yeah. Oh. So if I have
Where is this thing I wrote today?
Today, that's the one.
Magma, semigroup, and monoid.
Oh, okay. Okay. So then, if it's not a semigroup, I cannot have a monoid.
Come again?
If it's not a semigroup, I cannot have a monoid.
Where does semigroup go? Semigroup goes up to there. The operation is associative. Where does the magma go? Goes up to here. Only closed.
Well, basically, I'm saying.
Where
you're still answering it.
Yeah, where does monoid go. Monoid starts from here, covers all these problems. So now it's the monoid is demanding more. That's why I said the magma was a primitive one. So then, so if now we've got semigroup, we've got monoid, we're still going a journey ahead. We're going to be talking about the group. You see, at this stage, these structures are basically algebraic in terms of that they are structures which arise in terms of operations. Or apart from that, I said you must check whether if there's a neutral element, can there be two?
Yes.
Okay. Then
So this
try to prove that.
I think this is the case where we have to show that if there are two, they should be the same. Something. I'm not sure.
Yeah, that sounds good.
Okay.
That sounds good. So you construct a proof which says, okay, like what you're saying, assume that maybe there are more than two. Then you work with it based on the assumptions. Then somewhere they must give you a contradiction. Or they must just confirm that there are these things equal. Altogether. Okay. So the other thing which I wanted to add to that task, you then find examples of monoids. In this case, find as many as possible, including the ones I don't know myself. Talk.
If I talk about the whole numbers
Which one?
with addition, is it a monoid?
Whole numbers with addition, is it a monoid? If you talk about whole numbers with addition, in this case we're talking natural numbers with zero.
Yes.
Then you have to identify the neutral element and show that it behaves like a neutral element.
Zero.
Yeah, that's good. Right, forget about addition. Get another monoid from natural numbers.
And in this case, I'm forgetting about
addition. But
multiplication.
Huh? What did you say? I didn't hear what you said.
If I talk about multiplication.
And then we must identify the neutral element and show us that it's a neutral element.
1.
That sounds good. That sounds good. So now the thing is check what I'm saying. Yes.
If then maybe let's give an example with integers. What can I say with them then? Yeah.
I think you can see that the integers are a more bigger universe of these things. It's possible that more things could happen there. So what I advise you now, just pick the integers for a while. Pick the integers for a while. Okay. You can think of the natural numbers that we've done. Think of the positive fractions.
Okay.
You can remember the whole numbers are positive integers.
Yes.
No, non-negative integers, yeah. Then you can think about the rationals positive, integers positive, and the real numbers, though we don't know what are real numbers. Real numbers positive, and look at those things in respect to these structures which you have just.
So, okay. Can I ask this one? So then, if I think about two elements, in which if I put any operation between the two and they give me that special element, will I be getting out of this whole thing? What I'm basically saying is, I can if I pay a special element. And any other, I'll always get that other element. So now I'm thinking, if I pay two numbers and I get a special, what do I call it?
It depends on how you pay two numbers, but you are operating with them. Depending how you operate with them, then you can say what you want. I don't know. I'm not very clear what I'm asking, but if you take any two, the operation is already defined. So if you take two of them, you must interact them according to the operation.
Okay.
So the other one which I wanted to check with you, whether this is a magma, the usual one, which you use counting in grade 1, the usual 0, which you use counting in grade 1, And then if we take this, is it a magma?
Yeah.
What I'm trying to do here, we're trying to develop a sense of how do you check that a structure actually satisfies the axioms it's supposed to be to satisfy. So now we're taking addition, there's a usual addition, and 0 and 1, the usual 0 and 1. Then you're checking, is this a magma?
Okay. So please bring me back if I'm overramping.
No, that's the reason why we're discussing.
Right. So this is what I have read. And then I want to know if it's a magma. So it means that if I make this operation, I want it to still be.
Yeah.
But I know that this is that which is in there. Yes, I know that 0 plus 1 is 1, which is still in there. Yes. And also still 1 plus 0 is 1, which is still in there. So this operation gives me something that is already in there. So it is a magma. It is closed.
Let's do this. Let's do this. I'm showing you a trick here which you can use to do some of these things. 0, 1,
0,
1. 0 plus 0 gets 0. 0 plus 1, you get 1. 1 plus 0, you get 1. 1 plus 1, you get 2. Boom!
So you're telling me that, you're showing me that you're actually bringing me back to say that I can operate one element with itself. See if it's still in there.
It's still an element. Suppose I was picking these elements without having my eyes closed. I go there, I pick an element, I go there. I can end up having 51 and 1.
Why are you doing this?
So you see now, we've covered that. Now, for me, the idea is for your own enrichment. Listen to me very, very, very well. Very well. I've got my own mistakes about my own career. I know them. But you see, my mistakes, for me, they're supposed to be lessons for other people. Yeah. If you really want to be in mathematics, walk thinking mathematics, sleep thinking mathematics, eat thinking mathematics. So sometimes you take just a book. You talked about mathematics, you talked about this single. Read books in algebra. Like for example, today I was reading this book. What this book is got all the structures. Maybe magma you're not going to get it here because these are textbooks in schools. They start from a certain point, blah blah blah. You might get that kind of thing, but definitely other things, like we mentioned, you can Google them and find them. Read them more. Just open write your own notes. You can read and make sure that these things they can sink into your system. So when people are speaking these things, you feel like these things are part and parcel of you.
I can relate with them.
You can relate with them. So then if somebody says something which relates to you but is interesting, then the person can run and do some kind of research that can say, guys, I've seen this and this and this, come and talk about it. Then that's it.
You see with this one, you show me or you can ignore just a small information which is very important.
That's exactly what happened. You must make sure that you've covered all every stone and attended. You've seen that every time has been turned down.
Wow.
So now I'm telling you, you can take any book of algebra. You can read up to morning.
Yes. Sure. Corey, you can make something like this big and just shrink it like. Oh, okay.
And you can see the way I came up with the knowledge, the way I came up with the symbol. I didn't give it a definition. I worked with things. Then we see what happens. Then we say,
how does it behave?
Yeah, if it behaves this way, we call it symbol. If it behaves this way, we call it magma. If it behaves this way, we call it this and this. But you must see that the primitive things are always present in the modern things.
Okay.
If you can take it as a timeline, that 0 point is set,
Mm.
and then magma is number 1, semigroup number 2, monoid number 3.
Mm.
So all that kind of things. And I'm telling you the truth, man. If you can understand the theories of monoids and the groups and other things, you can immediately go into particle theory.
Sure.
Immediately, you can turn to particle theory.
Could it be that these things are challenging maybe elsewhere because they are just introduced by names and you don't even know?
The way, maybe the way they are introduced and the way they are engaged, that's a big problem. So I think our discussion for today will end here.
Sure.
And then we'll take the recording and cut it a bit, remove some of the conversations, sideline conversations, and then you can refer to it.
Yeah,
later.
definitely. This is interesting, sir. Thank you. Thank you.